Lesson: Model Interpretability Techniques. Model interpretability techniques are essential in the field of explainable artificial intelligence as they enable practitioners to comprehend and trust the outputs of complex machine learning models. As AI systems increasingly influence critical decision-making processes, interpretability has become a pivotal concern, particularly in high-stakes domains such as healthcare, finance, and autonomous vehicles. This lesson delves into the actionable insights and practical tools that professionals can employ to enhance their proficiency in model interpretability, facilitating the implementation of transparent and accountable AI systems. Understanding the internal workings of a machine learning model is crucial for validating its predictions and ensuring compliance with ethical and regulatory standards. One of the fundamental techniques for model interpretability is feature importance analysis. This approach involves quantifying the contribution of each input feature to the model's predictions. Tools like SHaP and Lime offer practical solutions for assessing feature importance. SHaP values, grounded in cooperative game theory, provide a unified measure of feature impact by distributing the prediction difference between the actual output and a baseline among the features. Lime, on the other hand, approximates the model locally around the prediction of interest using simple interpretable models, thus shedding light on the reasoning behind individual predictions. Implementing SHaP and Lime in real-world scenarios involves several steps. For instance, when utilizing SHaP, practitioners must first train their model and then calculate SHaP values for each feature concerning a specific prediction. These values can be visualized through summary plots, which present the average impact of each feature across the dataset, helping to identify global patterns in feature importance. Additionally, dependence plots can illustrate the effect of a single feature on predictions, conditional on other features. Lime requires the selection of a prediction to explain, followed by the generation of a perturbed dataset around the prediction instance. The model's outputs on this dataset are then used to fit a simple interpretable model, such as linear regression, to highlight the most influential features. Beyond feature importance, model interpretability can also be achieved through surrogate models. These are simplified models that approximate the behavior of a complex model, offering a more interpretable representation. Decision trees, for example, can be used as surrogate models to mimic the decision boundaries of a neural network. By training a decision tree on the predictions of the complex model, practitioners can gain insights into how the model partitions the feature space to arrive at its predictions. This approach is particularly useful for understanding ensemble methods like random forests or gradient boosting machines, which comprise multiple base learners. Another powerful technique for enhancing model interpretability is partial dependence plots. PDPs illustrate the relationship between a target outcome and a set of input features, marginalizing over all other features. This visualization helps practitioners understand the average effect of a feature on the model's predictions, thereby providing a clear interpretation of feature interactions and nonlinearities. Implementing PDPs involves selecting the features of interest and computing the model's predictions over a grid of feature values, holding other features constant. The resulting plot displays the predicted outcomes as a function of the selected features, offering actionable insights into feature importance and interactions. Counterfactual explanations are also gaining traction as an interpretable AI technique. They provide insights into what changes need to be made to an input instance to alter the model's prediction to a desired outcome. This method is particularly useful for instances where users wish to understand the decision boundary of a model. For example, in a credit scoring application, a counterfactual explanation might show that a slight increase in income and a reduction in debt would result in a loan approval. Implementing counterfactual explanations requires generating a set of alternative input instances and evaluating how changes in feature values affect the model's predictions. This approach not only enhances transparency, but also empowers users to take actionable steps towards achieving favorable outcomes. Case studies further underscore the practical utility of these interpretability techniques. In healthcare, for instance, SHaP has been used to elucidate the predictions of machine learning models in diagnosing diseases. By identifying the most influential clinical features, practitioners can validate model predictions and ensure that they align with established medical knowledge. Similarly, Lime has been employed in financial services to interpret credit risk models, allowing for transparent decision-making and improved trust among stakeholders. Statistics also illustrate the growing importance of model interpretability. A survey conducted by McKinsey & Company revealed that 40% of companies consider lack of interpretability a significant barrier to AI adoption. This highlights the critical need for professionals to engage with interpretability techniques, ensuring that AI systems are not only accurate, but also transparent and trustworthy. In conclusion, model interpretability techniques are indispensable tools for professionals seeking to implement explainable AI solutions. By leveraging feature importance analysis, surrogate models, partial dependence plots, and counterfactual explanations, practitioners can gain a deeper understanding of complex models, fostering transparency and accountability. Practical tools and frameworks, such as SHaP and Lime, provide actionable insights that enhance model interpretability, enabling professionals to address real-world challenges effectively. As AI continues to permeate various sectors, the ability to interpret model predictions will remain a key competency for ensuring ethical and responsible AI deployment.